Welcome back to lecture 19.4, where we're going to discuss the third law of thermodynamics. Okay, so this is probably my favorite of the laws of thermodynamics, and we've actually already seen the third law come into place. We've been talking about how, for example, the ideal gas with constant heat capacity had this negative infinity as we went to t equals 0. And that's just an unphysical situation. You can't have a negative infinity. And that came from that constant heat capacity that we took out of the integral when we calculated the entropy. So we said, really what has to happen is to balance that negative infinity, right? To balance that heat capacity dt over t, right? When this was for an ideal gas, we said it was n CV log Tf over T0. So this was the problem, that if Tf went to 0, then delta S for an ideal gas, then S went to negative infinity, right? So this logarithm is powerful singularity, right? So to get rid of that, we had to have our heat capacities go towards 0 as t goes to 0. And the result is that the entropy is always going to go towards 0 as t goes to 0. And this is already now the statement of the third law. Okay? But there's in fact two forms that were independently formulated for the third law of thermodynamics. Okay? And the first one is attributed to Nernst. And he said that as t goes to 0, that delta S goes to 0. That is, as I go towards 0, my changes in my entropy must go towards 0. But Planck said a statement which was, I think there's a C, P-L-A-N-C-K, that as t goes to 0, the entropy itself must go to 0. And this is actually somewhat of a stronger statement. So originally this idea was that at t equals 0, so Planck's idea was that at t equals 0, everything will become perfect. So a crystal would become perfect with no thermal motion, and so it's so perfect that there's well, I don't like the idea of disorder. Some people would say there's no disorder. So that's one way to think about this entropy. Another is that there's only one possible place for each atom to be. There's no other configurations. And so that's the way you think about it in StatMac. So therefore, the total entropy of the system would be 0. It's really a beautiful idea that things become perfect at t equals 0. I kind of really like that. And that it's kind of philosophical that only at t equals 0 can we have this kind of perfection. And at any finite temperature, we always have some thermal effects which are making systems imperfect. I really like that. Okay, so the question is, these are two forms of the third law. Are they the same? Are they the same thing? Okay, so remember, imagine a reversible process where I can write my ds as dq r over t. And then what I want to do is I want to calculate the delta s. So I want to integrate ds. Well, that's simply going to be the integral of dq over t. But if I do this as an indefinite integral, I really should add an integration constant, right? Now, if we don't really know what this integration constant is, but you can see that if this term goes to 0, right? So we can have delta s is s plus this s0. And so if we set this integration constant is equal to 0, then both of these third laws are consistent, right? So if we say that the background change, we say at t equals 0, s equals delta s equals 0, then our integration constant was 0. So we can really now say, oh, all these changes in entropy we've been talking about, there's a change with respect to some universal value. And the third law now really gives us that universal value. It says that at 0 temperature, the entropy should be 0. So now we know the baseline entropy. It's 0, okay? So I love this idea. So I love the idea that the entropy must go to 0 as t goes to 0. And I'll take it a step further and say something that the third law doesn't say. Nature prefers your entropy go to 0 as fast as it can. So we want the entropy to go to 0 as fast as it can as t goes to 0. Nature prefers you to remove all the entropy of a system if you can. And so what happens is, an ideal gas doesn't exist. Even metals where the heat capacity is linear in temperature, we talked about in the last lecture, 19.3, they don't go to 0 fast enough for the third law to be really happy, for nature to be happy. So they transition into this superconducting state where the heat capacity is dropping even faster, so the entropy is dropping even faster. So a lot of the fun of low temperature physics to me is to combine this idea of we build tools that go towards absolute 0, and then what we see is a whole rich plethora of new phase transitions that occur because nature wants entropy to go to 0 as fast as possible. And the state that you're in may not transition fast enough. So often you can actually sniff out these impending phase transitions if the entropy is too high. If the entropy is too high in a system as you're cooling down, you can pretty much be assured that it's going to transition into a new state where it's going to have lower entropy, but also that as you undergo that phase transition, because you're removing the latent heat, right, your dq is going to be 0, so your delta S is going to be 0, or negative. Sorry, your dq is going to be negative, so your delta S is going to be negative. You're going to have to actually decrease the entropy when you undergo a phase transition. You actually remove a bunch of heat from the system. You actually get that entropy to go down as fast as it can as t goes to 0. So I think that's a really fun thing to think about. And one of the reasons I'm so passionate about low temperature physics is because you really get this beautiful example of the third law. Okay, so next time we'll continue talking about this in lecture 20.